about one of the most powerful forces humans have ever learned to harness: nuclear energy. It begins inside the smallest building blocks of matter, the atom. At the heart of every atom sits the nucleus, a tight knot of protons and neutrons. And hidden in that knot is an astonishing secret: the strong nuclear force, which binds it all together. When that balance is broken or changed, a small bit of matter transforms into a vast amount of energy. That's the essence of nuclear power. There are two main ways this happens. One is fission, the splitting of heavy atoms like uranium or plutonium. The other is fusion, the joining of light atoms like hydrogen. Fission is the method we use today in our power plants. Fusion, the same process that powers the sun, is still a dream we chase for the future. To understand fission, imagine this. A neutron strikes a uranium-235 nucleus. The nucleus quivers, splits into two smaller pieces, and with a flash of invisible energy it sends out more neutrons. Those neutrons strike other nuclei, and the reaction cascades like dominoes falling, one after another. This is the chain reaction, the heartbeat of a nuclear reactor. Of course, something so powerful must be carefully controlled. That's where control rods come in. Made of special metals that absorb stray neutrons, these rods can be lowered or raised inside the reactor core to slow the process, speed it up, or stop it altogether. It's like gently applying the brakes on a powerful engine. And what is all that energy used for? In the end, it boils water. The heat from fission turns water into steam. The steam spins great turbines, and the turbines generate electricity. At its heart, a nuclear power plant is a very advanced kind of steam engine, but instead of burning coal, it unlocks energy from the atom. Now, let me pause the science to tell you a story. In 1954, in a small town in Russia called Obninsk, the world's first nuclear power plant came to life. It wasn't huge. It lit up only a few buildings and a small grid. But for the people who saw those first electric lights glow, it was magical. Just 9 years earlier, the world had witnessed the terrible destructive power of nuclear weapons. Now, here was proof that the atom could also bring warmth, light, and hope. Obninsk became known as the birthplace of the peaceful atom. Back to the science. If fission is today's reality, then fusion is tomorrow's promise. Deep in the sun, hydrogen atoms fuse into helium, releasing the light and warmth that touches our Earth. Scientists dream of recreating this miracle on Earth. To do so, they must heat hydrogen to over 100 million degrees Celsius, hotter than the sun's surface, and hold it there long enough for fusion to occur. Enormous machines called tokamaks use magnetic fields to trap the plasma. Giant lasers in inertial confinement experiments try to squeeze it for a fraction of a second. Projects like ITER in France are global collaborations, where dozens of countries work together to see if sustained fusion can be achieved. If successful, fusion could give us nearly limitless energy, with little waste and no greenhouse gases. But with fission, which we already use, there are risks. Nuclear fuel and its byproducts emit radiation unseen, but potent. Workers and engineers shield themselves carefully, and the reactor buildings are encased in thick domes of concrete and steel. Still, accidents have happened. In Chernobyl, in 1986, a flawed design and human mistakes led to an explosion that spread radioactive clouds across Europe. In Fukushima, in 2011, a massive tsunami disabled cooling systems, leading to meltdowns. And in 3 Mile Island, in 1979, a partial meltdown frightened the world even though little radiation escaped. These disasters were rare, but unforgettable. Since then, reactor designs have grown safer. Many modern systems use passive safety, meaning that if trouble starts, physics itself helps shut the reactor down without human intervention. There are environmental sides to the story, too. Nuclear energy produces almost no greenhouse gases during operation. It doesn't dirty the air with soot or fill the skies with smog. A single plant can power millions of homes, using far less land than solar or wind farms would need. But there's a cost. Reactors require large amounts of water for cooling, and the waste, though small in volume, remains dangerous for thousands of years. Economically, nuclear is a paradox. It's expensive to build a plant, often billions of dollars and years of effort. But once running, fuel is cheap, and the electricity is steady and reliable. Eventually, though, reactors must be shut down, dismantled, and cleaned up, a process that itself can take decades and cost as much as building the plant in the first place. On the global stage, nuclear energy is deeply tied to politics. The same knowledge that powers homes can also make weapons. That's why the International Atomic Energy Agency, the IAEA, carefully monitors nuclear programs. Some people see nuclear energy as a key tool to fight climate change, while others fear its dangers and want to leave it behind. And yet, the story of nuclear energy has its wonders. Reactors don't just make electricity. They also create radioisotopes that doctors use to scan for cancers and treat disease. Nuclear power lets submarines travel for months under the sea without surfacing, and aircraft carriers sail for decades without refueling. Far away in space, little nuclear batteries called RTGs keep probes like Voyager humming along, sending whispers back to Earth decades after launch. Some nations dream of using thorium instead of uranium, a more abundant element that produces less long-lived waste. Others explore small modular reactors, compact designs meant to be safer and cheaper. And in private labs and startups, scientists race to bring fusion to life, hopping to make energy as abundant as starlight. And finally, a cosmic thought. The uranium inside today's nuclear plants, the very atoms we split to light our homes, were forged in ancient explosions, supernovae and neutron star collisions, billions of years ago. Every time we switch on a lamp powered by nuclear energy, we are borrowing light from the heart of dead stars. So nuclear energy is not just science. It is history, politics, medicine, exploration, risk, and promise. It has dark chapters and bright ones. And like all powerful tools, it is up to us to decide how it will be used in the future.